Great. Thank you, Dave, for that introduction. So today I'm presenting on 3D synthetic aperture and steering for CSEM. And CSEM, or Controlled Source Electromagnetics, is a geophysical method used for finding hydrocarbon reservoirs in marine settings. A CSEM survey is conducted by a boat towing a horizontal electric dipole over receivers placed on the ocean floor. And the signal from the source travels down through the conductive subsurface and finds the resistive reservoirs. Now, there are some limitations to this method that keep it from being fully utilized in industry. And the first is because we have a conductive subsurface and the source is operated at low frequencies, the EM field is diffusive. This means that it's a very small part of the signal that contains information about the reservoir. And because of that, the lateral extent of the reservoir needs to be large enough when compared with the depth of burial to be detected. CSEM also has low spatial resolution when compared to other geophysical methods, such as seismic. So these drawbacks prompted an investigation into how to enhance the signal from the reservoir. And the technique that we propose to do this is synthetic aperture and steering. So this is the result of applying a 2D synthetic aperture source to some CSEM data. Here we're looking at a mapped view of the values of the receivers on the ocean floor. And the black square outlines the reservoir. And the value here is the ratio between the absolute value of the inline electric component of the field with the reservoir over the absolute value of the inline component of the field without the reservoir. And throughout the presentation, you'll hear me refer to the field with the reservoir as the pay field, and the field without the reservoir as the wet field. So we can then apply steering to our synthetic aperture source, and this is the result. And we've increased our value here, which is that ratio. And so now I want to show you how we apply synthetic aperture and show you results with some synthetic data. So the basic idea of synthetic aperture, which is an idea borrowed from the radar field, is to take multiple individual sources and add them together to create one large source. And because we're adding these individual sources, we can apply weighting to the sources before we add them together to steer the source. And the process is summarized in this equation, where an individual source is multiplied by weighting terms and then summed with the other sources we're using in our synthetic aperture. So here, S sub j is the location of an individual source, and R is the location of the receivers. And F represents the response for a single source at a single frequency omega. And F can be any component of the electric or magnetic field. Delta psi here is the phase shift, and A is what we call the energy compensation term, which we use to account for the rapid decay in the field and the differences between individual sources. So I'm going to show you how we apply synthetic aperture to some noiseless synthetic data, which was provided to us by Shell's EM research group. This is the Earth model for the synthetic data we have. It's a layered anisotropic model with resistivities that are typical of a marine subsurface. The reservoir is 4 kilometers long in both the inline and crossline directions and 50 meters thick. It's 1.5 kilometers below the ocean floor. And there's a 2 kilometer water layer that's included to dampen the effect of the air wave. And our source is a 300 meter horizontal electric dipole with a frequency of 0.2 hertz. And we have the data for this model with the reservoir and without, for all three components of the electric and magnetic field. The survey geometry, which I'm showing here in a map view, follows the typical geometry of a CSEM survey. There's 5 parallel tow lines that are centered over the reservoir, which is shown here as the black square. In each of these tow lines, there's 100 source locations. But unlike a typical CSEM survey, we have sampling points within a 3D volume from the top of the water layer down to 4 kilometers depth. And the coverage of them in the map view is shown here as the gray rectangle. And we do that so that we can see the changes in the field at depth. And I'm going to show you examples of applying synthetic aperture to this 2D source shown in red. It's purposely offset from the reservoir so that I can show you the benefits of inline and crossline steering. And this 2D source is composed of 51 individual sources distributed over 3 tow lines. So before I show you the results using this 2D source distribution, I first want to show you data from just a single source. Shown here is the red dot. Again, the reservoirs, the footprint of the reservoir is outlined by the black square. And this is the response of the receivers on the ocean floor. And again, the value is the ratio between the absolute value of the electric pay field over the absolute value of the electric wet field. And you can see that the maximum of this field is offset from the source. And that's because it's larger source receiver offsets that contain information about the reservoir. So now we can apply synthetic aperture to the 2D source distribution I showed you earlier, and this is the result. So we haven't steered this source yet, but you can see that we've already increased the value, the maximum of our ratio. So now we can apply steering to these sources to try to achieve a better result. But how do we know what steering angles we should steer all these sources at? And what energy compensation terms should we use? Well, we find those by going through an optimization scheme. And in this optimization scheme, we define the best steering parameters that maximize the ratio between the pay and the wet fields. And we do that by testing different combinations of 4 parameters. 2 are steering angles, theta and phi, for the inline and crossline directions, respectively, and 2 weighting terms, A sub I and A sub C. And so we go through that process and test these different combinations. But we don't want to find this maximum at a single value, because it could just be an erroneous data point. We want to find the maximum of the ratio over a spatial area to ensure that we're enhancing the signal from the reservoir. And we define that area by looking back at the single source. So this single source is located within the center of that 2D source distribution that I've used. And so we define this area that we expect to see the anomaly as this dashed box shown here. So we go through the process of finding those optimal steering parameters, and this is the result. And the steering parameters are listed there at the bottom. And the angles that we find for theta and phi are reasonable for the source reservoir geometry that we have. And so now we can compare this result to the single source, an unsteered result. So the average value in this dashed box is around 2. And I've clipped the color bar here so we can compare them. So don't let that confuse you. But so this value, this average value 2 that we have in the dashed box is equivalent to 100% detectability of the reservoir. And we can compare that to the single source, which has an average value in the dashed box of 1.1, or 10% detectability, and the unsteered source, which has an average ratio in the dashed box of 1.19 or 19% detectability. So it looks like that we've applied the synthetic aperture and steering, and we've actually changed the direction that the energy is moving, and we've sent it more into the direction of the reservoir. But we can't really conclude that from this image because this is just showing you the magnitude of an electromagnetic field. But one measure that does show, that can tell us something about the direction is the Poynting vector, or the energy flux density of an electromagnetic field. And this is found by cross-multiplying the electric and magnetic field. And for EM fields in the frequency domain, we average this value over time to remove the effect of the oscillating source. So I'm going to show you some 2D slices along the yellow line shown here, which is in the crossline direction. So this is the 2D time-averaged normalized Poynting vector for a single source shown in red. The ocean floor is denoted by the green line, and the reservoir is shown as the black rectangle. So looking at this 2D Poynting vector, it really shows us the different parts of an electromagnetic field. So there's the energy that radiates away from the source, and some of it travels upward to hit the top of the water layer and come back down as the air wave. And another part travels downward into the subsurface and through the reservoir and back up. And that's what gives us the information about the reservoir. And you can see here that the orange circle is highlighting how some of the energy is actually radiating away from the reservoir. So we can apply a synthetic aperture. And again, this is in the crossline direction. So here our sources are sparsely spaced. But even with that broad spacing, you can see that when we add these sources together, we're changing the direction to a more downward trending direction, which is what's highlighted there by the orange circle. But it's still not in the direction of the reservoir. So we can finally apply our optimal steering parameters to this source. And now you can see that within this orange circle, we have indeed changed the direction of this energy to move towards the reservoir. Also, you can see that more of the energy is traveling along the lateral direction of the reservoir, which basically means that more of the data that we record will have that information about the reservoir. So because we have all three components of the electric and magnetic field, we can also look at the Poynting vector in 3D. So this is the 3D time-averaged normalized Poynting vector. And here I'm just showing the downward going energy. So you're not seeing the water layer here. And so this is really shows us how the energy is propagating from the source, which is shown as the blue rectangle, down through the reservoir, which is here is the black rectangle. And so this Poynting vector really is a diagnostic tool that allows us to helps us ensure that the steering parameters we've chosen are actually changing the direction of the energy and boosting the signal from the reservoir. So far I've shown you how we apply synthetic aperture and how we find some optimal steering parameters, and then how we make sure that these are the best parameters for the survey. However, there are some issues with that optimization I showed you. One of the first being that you have to test these different combinations of parameters, which for a large 2D source distribution really isn't feasible. Also, another issue is with the type of weighting we apply. So this is a simplified form of the synthetic aperture equation I showed you earlier. And The weighting we use is exponential, and that's the A and delta psi you see here. And a requirement that we apply for these parameters is that they be linear in the space coordinates. And this creates a plane wave that propagates. But that may not be the best type of steering for every survey. So we looked at using a more general weighting, which is shown here as A sub j. And it's just a single complex number multiplied to each individual source. And here there's no limit placed on the phase or amplitude of these A sub j's. But now we have to find an A sub j for each individual source that we used. So it leads to a new formalization of our optimization scheme. So now instead of maximizing the ratio, we want to maximize the difference between the field with the reservoir and without. And here I'm showing the field with the reservoir as S and the field without the reservoir as S naught. And again, similar to the other optimization, we want to maximize this difference over the area where we expect to see an anomaly. And another part of this is that we have to place a constraint on A sub j so that it doesn't arbitrarily increase the amount of energy emitted by these sources. So here we just constrain it to equal 1. Another way to describe this optimization is pictorially, and this also sort of describes how we solve this problem. So our constraint that we place on A sub j is equivalent to the equation of a sphere, and the difference, which is what we want to maximize, is the equation of an ellipse. And our optimal weights are going to be at the intersection of this sphere and ellipse. And I'm just showing them here as 2D images, but we're working with these at higher dimensions. And so the way we go about finding this vector A, shown in blue, is to put our problem in quadratic form. And then we rotate the axes of the matrices to the principal axes. And then we find the largest eigenvalue that corresponds, we find the largest eigenvalue of that matrix. And then our optimal steering parameters will be the eigenvalue the eigenvector that corresponds to that eigenvalue. And we have just begun to implement this, and so I don't have any results to show you today, but we know that first of all, it's a linear problem, so it's much easier to solve, and it'll be able to find the exact values, hopefully, that will maximize this difference. So I would like to summarize by saying that if we're able to apply synthetic aperture and steering to CSEM, that hopefully it will benefit the method, and we'll be able to cement CSEM's place in industry. And I would like to acknowledge my fellow CWP students for their discussions. And I would also like to acknowledge our co-authors on this research, Fawn and David. And finally, I would like to thank the Shell Game Changer Project for funding for this research. Thank you, and